Okay, so let us continue our discussion on the computer vision. When we say computer vision, it is a field of artificial intelligence that's focused on enabling machines to interpret and understand visual information from the real world. Again, it is a field of artificial intelligence that is focused on enabling machines to interpret and understand visual information. Okay, so here are the scopes of computer vision. We have image understanding, scene understanding, object recognition, image segmentation, and activity recognition. When we say image understanding, it is the analyzing and interpreting of the contents of images to extract meaningful information. So, iniintindi ng computer natin kung ano ba ang meron sa images na yon. Next one is scene understanding. It is the understanding the context and relationships within a scene depicted in images or videos. Okay? So basically ito yung meron tayong bundok, meron tayong sun, meron tayong clouds. That's scene understanding. Okay? The next one is object recognition. It is the identifying and classifying objects within images or videos for various applications such as autonomous driving and surveillance. So when we say object recognition, it recognizes various images or objects. For example, kung mapapansin nyo sa Tesla, no, na-identify nila kung car ba siya, kung truck ba siya, kung van ba siya. So that's object recognition. When we say image segmentation, no, it is partitioning or dividing images into meaningful regions for tasks like medical imaging and image editing. That is image segmentation. Pinapartition natin images parang sa ganun, makita natin kung ano ba or makita natin yung mga meaningful portions ng images for tasks like medical imaging and image editing. Last one is activity recognition. When we say activity recognition, it is recognizing human actions and activities in videos for applications like video surveillance and sports analysis. So, kung mapapansin ninyo, wala pala tayo nung ibang video, no? Anyway, if you can remember yung video natin last time, yung activity recognition kung saan nakikita nung computer kung ano yung bola, kung ano yung human, natitrace nila kung saan papunta yung human, saan papunta yung bola, diba? So that's activity recognition. To further understand the following ideas, we have here the fifth video.
Hi, I'm Carrie Ann and welcome to Crash Course Computer Science. Today, let's start by thinking about how important vision can be. Most people rely on it to prepare food, walk around obstacles, read street signs, watch videos like this, and do hundreds of other tasks. Vision is the highest bandwidth sense, and it provides a fire hose of information about the state of the world and how to act on it. For this reason, computer scientists have been trying to give computers vision for half a century, birthing the subfield of computer vision. Its goal is to give computers the ability to extract high-level understanding from digital images and videos. And as everyone with a digital camera or smartphone knows, computers are already really good at capturing photos with incredible fidelity and detail, much better than humans in fact. But as computer vision professor Fei-Fei Li recently said, just like to hear is not the same as to listen, to take pictures is not the same as to see. As a refresher, images on computers are most often stored as big grids of pixels. Each pixel is defined by a colour stored as a combination of three additive primary colours, red, green and blue. By combining different intensities of these three colours, we can represent any colour, which are called RGB values. Perhaps the simplest computer vision algorithm and a good place to start is to track a coloured object like a bright pink ball. The first thing we need to do is record the ball's colour. For that, we'll take the RGB value of the centremost pixel. With that value saved, we can give a computer program an image and ask it to find the pixel with the closest colour match. An algorithm like this might start in the upper right corner and check each pixel one at a time, calculating the difference difference from our target colour. Now, having looked at every pixel, the best match is very likely a pixel from our ball. And we're not limited to running this algorithm on a single photo. We can do it for every frame in a video, allowing us to track the ball over time. Of course, due to variations in lighting, shadows and other effects, the ball on the field is almost certainly not going to be the exact same RGB value as our target colour, but merely the closest match. In more extreme cases, like at a game at night, the tracking might be poor, and if one of the team's jerseys used the same colour as the ball, our algorithm might get totally confused. For these reasons, colour marker tracking and similar algorithms are rarely used, unless the environment can be tightly controlled. This colour tracking example was able to search pixel by pixel, because colours are stored inside of single pixels. But this approach doesn't work for features larger than a single pixel, like edges of objects, which are inherently made up of many pixels. To identify these types of features in images, computer vision algorithms have to consider small regions of pixels called patches. As an example, let's talk about an algorithm that finds vertical edges in a scene, let's say to help a drone navigate safely through a field of obstacles. To keep things simple, we're going to convert our image into grayscale, although most algorithms can handle colour. Now let's zoom into one of these poles to see what an edge looks like up close. We can easily see where the left edge of the pole starts, because there's a change in colour that persists across many pixels vertically. We can define this behaviour more formally by creating a rule that says the likelihood of a pixel being a vertical edge is the magnitude of the difference in colour between some pixels to its left and some pixels to its right. The bigger the colour difference between these two sets of pixels, the more likely the pixel is on an edge. If the colour difference is small, it's probably not an edge at all. The mathematical notation for this operation looks like this. It's called a kernel or filter. It contains the values for a pixel-wise multiplication, the sum of which is saved into the centre pixel. Let's see how this works for our example pixel. I've gone ahead and labelled all of the pixels with their grayscale values. Now we take our kernel and centre it over our pixel of interest. This specifies what each pixel value underneath should be multiplied by. Then we just add up all those numbers. In this example, that gives us 147. That becomes our new pixel value. This operation of applying a kernel to a patch of pixels is called a convolution. Now let's apply our kernel to another pixel. In this case, the result is 1, just 1. In other words, it's a very small colour difference and not an edge. If we apply our kernel to every pixel in the photo, the result looks like this, where the highest pixel values are where there are strong vertical edges. Note that horizontal edges, like those platforms in the background, are almost invisible. If we wanted to highlight those features, we'd have to use a different kernel, one that's sensitive to horizontal edges. Both of these edge-enhancing kernels are called Pruitt operators, named after their inventor. These are just two examples of a huge variety of kernels able to perform many different image transformations. For example, here's a kernel that sharpens images, and here's a kernel that blurs them. Kernels can also be used like little image cookie cutters that match only certain shapes. So our edge kernels looked for image patches with strong differences from right to left or up and down. But we could also make kernels that are good at finding lines with edges on both sides, and even islands of pixels surrounded by contrasting colours. These types of kernels can begin to characterize simple shapes. For example, on faces, the bridge of the nose tends to be brighter than the sides of the nose, resulting in higher values for line-sensitive kernels. Eyes are also distinctive, a dark circle surrounded by lighter pixels, a pattern other kernels are sensitive to. When a computer scans through an image, most often by sliding around a search window, it can look for combinations of features indicative of a human face. Although each kernel is a weak face detector by itself, combined they can be quite accurate. It's unlikely that a bunch of face-like features will cluster together if they're not a face. This was the basis of an early and influential algorithm called Viola-Jones face detection. Today, the hot new algorithms on the block are convolutional neural networks. We talked about neural nets last episode if you need a primer. In short, an artificial neuron, which is the building block of a neural network, takes a series of inputs and multiplies each by a specified weight, and then sums those values all together. This should sound vaguely familiar because it's a lot like a convolution. In fact, if we pass a neuron 2D pixel data rather than a one-dimensional list of inputs, it's exactly like a convolution. The input weights are equivalent to kernel values, but unlike a predefined kernel, neural networks can learn their own useful kernels that are able to recognize interesting features in images. Convolutional neural networks use banks of those neurons to process image data, each outputting a new image essentially digested by different learned kernels. These outputs are then processed by subsequent layers of neurons, allowing for convolutions on convolutions on convolutions. The very first convolutional layer might find things like edges, as that's what a single convolution can recognise, as we've already discussed. The next layer might have neurons that convolve on those edge features to recognise simple shapes comprised of edges, like corners. A layer beyond that might convolve on those corner features and contain neurons that can recognise simple objects like mouths and eyebrows. And this keeps going, building up in complexity until there's a layer that does a convolution that puts it together. Eyes, ears, mouth, nose, the whole 9 yards, and says, aha, it's a face. Convolutional neural networks aren't required to be many layers deep, but they usually are in order to recognise complex objects and scenes. That's why the technique is considered deep learning. Both Viola-Jones and convolutional neural networks can be applied to many image recognition problems, like recognising handwritten text, spotting tumours in CT scans, and monitoring traffic flow on roads. But we're going to stick with faces. Regardless of what algorithm was used, once we've isolated a face in a photo, we can apply more specialised computer vision algorithms to pinpoint facial landmarks, like the tip of the nose and corners of the mouth. This data can be used for determining things like if the eyes are open, which is pretty easy once you have the landmarks. It's just the distance between points. We can also track the position of the eyebrows. Their relative position to the eyes can be an indicator of surprise or delight. Smiles are also pretty straightforward to detect, based on the shape of mouth landmarks. All of this information can be interpreted by emotion recognition algorithms, giving computers the ability to infer when you're happy, sad, frustrated, confused, and so on. In turn, that could allow computers to intelligently adapt their behaviour, maybe offer tips when you're confused and not asked to install updates when you're frustrated. This is just one example of how vision can give computers the ability to be context sensitive, that is, aware of their surroundings. And not just the physical surroundings, like if you're at work or on a train, but also your social surroundings, like if you're in a formal business meeting versus a friend's birthday party. You behave differently in those surroundings, and so should computing devices if they're smart. Facial landmarks also capture the geometry of your face, like the distance between your eyes and the height of your forehead. This is one form of biometric data, and it allows computers with cameras to recognise you, whether it's your smartphone automatically unlocking itself when it sees you, or governments tracking people using CCTV cameras. The applications of facial recognition seem limitless. There have also been recent breakthroughs in landmark tracking for hands and whole bodies, giving computers the ability to interpret a user's body language, and what hand gestures they're frantically waving at their internet-connected microwave. As we've talked about many times in this series, abstraction is the key to building complex systems, and the same is true in computer vision. At the hardware level, you have engineers building better and better cameras, giving computers improved sight with each passing year, which I can't say for myself. Using that camera data, you have computer vision algorithms crunching pixels to find things like faces and hands. And then using output from those algorithms, you have even more specialized algorithms for interpreting things like user facial expression and hand gestures. On top of that, there are people building novel interactive experiences like smart TVs and intelligent tutoring systems that respond to hand gestures and emotion. Each of these levels are active areas of research, with breakthroughs happening every year, and that's just the tip of the iceberg. Today, computer vision is everywhere, whether it's barcodes being scanned at stores, self-driving cars waiting at red lights, or Snapchat filters superimposing moustaches. And the most exciting thing is that computer scientists are really just getting started, enabled by recent advances in computing like super-fast GPUs. Computers with human-like ability to see are going to totally change how we interact with them. Of course, it'd also be nice if they could hear and speak, which we'll discuss next week. I'll see you then. Hey guys, before I go, I wanted to tell you about a great new show from PBS Digital Studios, The Origin of Everything. In this series, host Danielle Bainbridge investigates the history of, well, everything, from the hashtag in US healthcare to Godzilla and even killer clowns. It's a show about how the complex intersections of our past have informed the world we know today, and I think you'll love it. Crash Course Computer Science is produced in association with PBS Digital Studios. At their channel.
Okay, so let's continue on the discussion about the traditional computer vision techniques. Huh? So we have here three techniques previously in the traditional way. Okay, we have here the limited adaptability, high sensitivity to noise, and manual feature engineering. When we say traditional computer vision techniques, it refers to the classical methods used for analyzing and processing visual data before the rise of deep learning. For example, it includes edge detection, feature extraction, and template matching. So that's traditional computer vision technique. Classical methods before the rise of deep learning. So when we say limited adaptability, as its limitations and challenges, uh, traditional methods often struggle with complex and variable environments where handcrafted features may fail to generalize. So that's limited adaptability. Okay, the next one is high sensitivity to noise. These techniques are sensitive to noise and variations in lighting conditions, yung mga ilaw. Okay, leading to unreliable results in real-world scenarios. And last one is manual feature engineering. It is designing effective features that requires expert knowledge and manual tuning, making the process labor-intensive and time-consuming. Dito, we have to request for experts' knowledge and manual tuning to provide effective features for computer visions, no? And making it a labor intensive and time consuming process. Okay, so these are the limitations and challenges of traditional computer vision techniques: the limited adaptability, high sensitivity to noise, and manual feature engineering. Okay, we also have here the roles of AI in advanced computer vision. We have the feature learning, robustness enhancement, automation, improved accuracy, scalability, and adaptability. So ano ba itong feature learning? AI algorithms automatically learn discriminative features from raw data, eliminating the need for manual feature engineering. Dito, AI algorithm na ang nag-aaral ng mga features mula sa iba't ibang raw data, removing or deleting the need for manual feature hunting, okay, or manual feature engineering. Okay, that's feature learning. Next one is robustness enhancement. AI now, improve the robustness of computer vision systems to variations in data, enabling more reliable performance in diverse environments. So AI enhances the robustness of computer visions, making it more reliable performance in diverse environment. Okay. Next one is automation. AI enables automation of tasks again, no? Such as object detection, recognition, and tracking, reducing human intervention and improving efficiency. Okay? So those are the advances of AI, no? Nakakatulong na siya sa pagde-detect ng mga object, pag-recognize ng mga patterns, di ba? Pagta-track ng mga object or human movements, okay? So that's automation. Nakakatulong na kaagad, di ba? So I have here improve accuracy. When we say improve accuracy, AI-based approaches often outperform traditional methods. Diba? Tama naman. Okay? Uh, in generalizing to a new data. Kapag ka kasi AI na, 'di ba? Nakakatulong siya instead of the use of human movements or human intelligence. Yung kasing AI na outperform nyo na yung mga traditional methods. Specifically kung pagka mayroong mga new data na natatanggap, nagiging mas advanced at mas mabilis ang generalization natin ng data using AI. Okay? Next one is scalability. When we say scalability, AI algorithms can scale to large datasets and complex problems, making them suitable for real-world applications with vast amounts of visual data. So sila, since they are learning from a large amount of data, kaya na nilang mag-scale pa na mas malaking datasets instead sa may human mind, a human vision, no? Siyempre, pagka hindi familiar sa isang object, alamin po natin 'to kung saan ba 'to related or saang family ba 'to naka-join na species, for example. When we say scalability, kahit gaano karaming images ang ilagay mo diyan sa AI, it can solve complex problems because of its vast amounts of visual data installed or learned by the computer with the help of AI. And last one is adaptability. AI models can adapt and learn from new data, allowing computer vision systems to continuously improve over time. So with the help of AI, nakukuha niya lahat kaagad ng mga idea, ng data na nakakatulong naman sa ating computer vision to improve over time. So that's the roles of AI in advancing computer vision: feature learning, robustness enhancement, automation, improved accuracy, scalability, and adaptability. So we have here neural networks in computer vision, the CNN, the RNN, and the GAN. When we say neural networks, no, in computer vision, neural networks are computational models inspired by the structure and function of the human brain. They consist of interconnected layers of artificial neurons that process input data to perform tasks like image classification and object detection. Okay, again, neural networks is like it is inspired by the structure and function of the human brain. Meron siyang interconnected layers of artificial neurons that processes input data to perform tasks like image classification and object detection. When we say convolutional neural network or CNN, it is specialized for processing grid structured data like images. CNNs use convolutional layers to extract hierarchical features from input images. So to further understand CNN, let us watch these two videos.
Okay, pop quiz. What am I drawing? I'm going to make 3 predictions here. Firstly, you think I drew a house. You'd be right. Secondly, that it just came really easily to you. It was effortless. And thirdly, you're thinking that I'm not much of an artist. And you'd be right on all counts there. But how can we look at this set of geometric shapes and think, oh, house. If you live in a house, I bet it looks nothing like this. Well, that ability to perform object identification that comes so easily to us does not come so easily to a computer, but that is where we can apply something called convolutional neural networks to the problem. Now, a convolutional neural network, or a CNN, is an area of deep learning that specializes in pattern recognition. My name is Martin Keane, and I work in the IBM garage at IBM. Now, let's take a look at how CNN works at a high level. Well, let's break it down. CNN, convolutional neural network. Well, let's start with the artificial neural network part. This is a standard network that consists of multiple layers that are interconnected, and each layer receives some input, transforms that input to something else, and passes it as output to the next layer. That's how neural networks work. And CNN is a particular part of the neural network, or a section of layers. Let's say it's these 3 layers here. And within these layers, we have something called filters. And it's the filters that perform the pattern recognition that CNN is so good at. So let's apply this to our house example. Now, if this house were an actual image, it would be a series of pixels, just like any image. And if we zoom in on a particular part of this house, let's say we zoom in around here, then we would get, well, the window. And what we're saying here is that a window consists of some perfectly straight lines. Almost perfectly straight lines. But you know, a window doesn't need to look like that. A window could equally kind of look like this, and we would still say it was a window. The cool thing about CNN is that using filters, CNN could also say that these 2 objects represent the same thing. The way they do that then is through the application of these filters. So let's take a look at how that works. Now, a filter is basically just a 3x3 block. And within that block, we can specify a pattern to look for. So we could say, let's look for a pattern like this, a right angle in our image. So what we do is we take this filter, and it's a 3x3 block here. We will analyze the equivalent 3x3 block up here as well. So we'll look at, first of all, these first group of 3 by 3 pixels, and we will see how close are they to the filter shape. And we'll give that a numeric score. Then we will move across one column to the right and look at the next 3 by 3 block of pixels and score how close they are to the filter shape. And we will continue to slide over or convolve over all of these pixel layers until we have mapped every 3 by 3 block. Now that's just for one filter, but what that will give us is an array of numbers that say how closely an image matches our filter. But we can add more filters. So we could add another 3 by 3 filter here, and perhaps this one looks for a shape like this. And we could add a third filter here, and perhaps this looks for a different kind of right angle shape. If we take the numeric arrays from all of these filters and combine them together in a process called pooling, then we have a much better understanding of what is contained within this series of pixels. Now that's just the first layer of the CNN. And as we go deeper into the neural network, the filters become more abstract, or they can do more. So the second layer of filters perhaps can perform tasks like basic object recognition. So we could have filters here that might be able to recognize the presence of a window, or the presence of a door, or the presence of a roof. And as we go deeper into the CNN to the next layer, well, maybe these filters can perform even more abstract tasks, like being able to determine whether we're looking at a house, or we're looking at an apartment, or whether we're looking at a skyscraper. So you can see the application of these filters increases as we go through the network and can perform more and more tasks. And that's a very high-level basic overview of what CNN is. It has a ton of business applications. Think of OCR, for example, for understanding handwritten documents. Think of visual recognition and facial detection and visual search. Think of medical imagery and looking at that and determining what is being shown in an imaging scan. And even think of the fact that we can apply a CNN to perform object identification for badly drawn houses. If you have any questions, please drop us a line below. And if you want to see more videos like this in the future, please like and subscribe.
What do you do if the patterns in your data change with time? In that case, your best bet is to use a recurrent neural network. This deep learning model has a simple structure with a built-in feedback loop, allowing it to act as a forecasting engine. Let's take a closer look. Recurrent neural networks, or RNNs, have a long history, but their recent popularity is mostly due to the works of Jürgen Schmidhuber, Sepp Hochreiter, and Alex Graves. Their applications are extremely versatile, ranging from speech recognition to driverless cars. All the nets we've seen up to this point have been feed-forward neural networks. In a feed-forward neural network, signals flow in only one direction from input to output, one layer at a time. In a recurrent net, the output of a layer is added to the next input and fed back into the same layer, which is typically the only layer in the entire network. You can think of this process as a passage through time. Shown here are 4 such time steps. At t equals 1, the net takes the output of time t equals 0 and sends it back into the net along with the next input. The net repeats this for t equals 2, t equals 3, and so on. Unlike feed-forward nets, a recurrent net can receive a sequence of values as input, and it can also produce a sequence of values as output. The ability to operate with sequences opens up these nets to a wide variety of applications. Here are a few examples. When the input is singular and the output is a sequence, a potential application is image captioning. A sequence of inputs with a single output can be used for document classification. When both the input and output are sequences, these nets can classify videos frame by frame. If a time delay is introduced, the net can statistically forecast the demand in supply chain planning. Have you ever used an RNN for one of these applications? If so, please comment and share your experiences. Like we've seen with previous deep learning models, by stacking RNNs on top of each other, you can form a net capable of more complex output than a single RNN working alone. Typically, an RNN is an extremely difficult net to train. Since these nets use backpropagation, we once again run into the problem of the vanishing gradient. Unfortunately, the vanishing gradient is exponentially worse for an RNN. The reason for this is that each time step is the equivalent of an entire layer in a feed-forward network. So training an RNN for 100 time steps is like training a 100-layer feed-forward net. This leads to exponentially small gradients and a decay of information through time. There are several ways to address this problem, the most popular of which is gating. Gating is a technique that helps the net decide when to forget the current input and when to remember it for future time steps. The most popular gating types today are GRU and LSTM. Besides gating, there are also a few other techniques like gradient clipping, steeper gates, and better optimizers. When it comes to training a recurrent net, GPUs are an obvious choice over an ordinary CPU. This was validated by a research team at Indico, which uses these nets on text processing tasks like sentiment analysis and helpfulness extraction. The team found that GPUs were able to train the nets 250 times faster. That's the difference between 1 day of training and over 8 months. So, under what circumstances would you use a recurrent net over a feed-forward net? We know that a feed-forward net outputs one value, which in many cases was a class or a prediction. A recurrent net is suited for time series data, where an output can be the next value in a sequence, or the next several values. So the answer depends on whether the application calls for classification, regression, or forecasting. In the next video, we'll take a look at a family of deep learning models known as the autoencoders.
Okay.
Okay, so let's continue on recurrent neural networks. When we say recurrent neural networks or RNN, it is suitable for processing sequential data. RNNs have recurrent connections that allow them to capture temporal dependencies in sequences. Kung dun sa convolutional networks is processed sila through grid structured data, no? Sa recurrent neural naman is sequential data. Okay? So that is RNN. The last one is generative adversarial networks. It is composed or it is comprising a generator and a discriminator network. These are used for generating realistic images and data by learning from a training dataset. When we say generative, again, no, they are comprising a generator and a discriminator, meaning they are used for generating realistic images and data by learning from training set. So these are the neural networks in computer vision: convolutional neural network, recurrent neural network, and generative adversarial networks. So how about deep learning algorithms for image recognition? We have here again CNN, RNN, but the last one has already changed, the deep belief networks or DBF. When we say deep learning algorithms for image recognition, no, deep learning, okay, Deep learning algorithms leverage neural networks with multiple layers to automatically learn hierarchical representations from raw image data. Okay? Again, deep learning algorithms leverage neural networks with multiple layers to automatically learn hierarchical representations from a raw image data. Okay? For example, we have here the CNN again, no? Designed specifically for image processing tasks. No? So that's how CNN is being used. No? Uh, these convolutional layers extract features from input images and perform tasks like image classification and object detection. The recurrent naman, it is suitable for again sequential data like text and speech. Okay? So they have recurrent connections that enable them to capture temporal dependencies and context and sequences. Okay? To further understand the RNN, let us watch the eighth
Recurrent
video.
neural networks, or short RNNs, are an essential part in deep learning. They are widely used and are incredibly effective in many different kinds of applications, especially in the field of natural language processing, like for text generation or text classification, but they can also be used when working with images or video data. So in this video we learn what RNNs are and how they work. This video is part of the Deep Learning Explained series by Assembly AI, which is a company that creates a state-of-the-art speech-to-text API. And if you want to try their API for free, then grab your free API token using the link in the description below. And now let's get started. First, let's have a quick look at one definition of RNNs. RNNs are a special class of neural networks that operate on sequence data and allow previous outputs to be used as inputs while having hidden states. So let us reiterate. They are also neural networks. They have something to do with hidden states, and they can keep track of previous outputs in a sequence. So if this definition is not clear for you right now, don't worry, we will come back to this in a moment. But first, let's have a look at why RNNs work so great. And for this, we look at one example. Let's do a quick test and complete this sentence. The color of the sky is blue. Or another one, I grew up in Germany, that's why I'm fluent in German. And I bet you guessed the correct word, because for our brains it should not be a problem to determine the missing word. And we know the word because we know the previous text. We don't just look at one word and throw away the previous information. We remember the previous context and then use this information. And this is exactly what RNNs do. So if we try to do this word prediction with a normal neural net, then this would not work, because one major shortcoming of neural nets is that they cannot keep track of previous outputs. And this is what RNNs try to fix. Now let's go back to the original definition. By now it should be more clear what is meant with sequence data and previous outputs. For example, a sequence data can be a sentence where the RNN looks at each word separately, encodes it to a mathematical representation, and can then remember the previous outputs. But how exactly does this work, and what are these hidden states? So a normal neural net gets an input, then has different hidden layers and returns an output. Now RNNs have loops in them, allowing the information to persist. So we can also unroll this loop and look at this picture in a different way. We can now interpret this as a sequence data with different time steps. We have the first input where we do calculations in the hidden layers and can then get an output. And then we pass the information from the hidden states onto the second time step. And here again we get an input, then we do calculations where we now can use the previous information, and then again can get an output and pass on the information, and so on. Now each time step contains the information from all previous steps, so the last step has information about all the previous context. And then, for example, we can use this very last output here and pass it on to a simple linear classification layer and do the word prediction like in the example from before. So by now I hope the explanation and motivation of RNNs is clear to you. Another reason why RNNs are so powerful is because of their flexibility. Now, normal neural nets or convolutional nets have the limitation that they don't remember previous states, and moreover, they accept a fixed size vector as an input and produce a fixed sized vector as an output. For example, one image can be the input and the probability of different classes is the output. So this is what we get with traditional neural networks, and recurrent neural nets, on the other hand, operate on sequence data. So they operate over a sequence of vectors, and this could be sequences in the input, the output, or in both. And this allows for many different applications. For example, we can have a one-to-many relationship, which can be used for music generation. So we get one input, but many outputs. We can also have a many-to-one relationship. So we have many inputs, but only one output. This is, for example, used for sentiment classification. And we can have different types of many-to-many relationships. For example, here for name entity recognition or for machine translation. And by the way, these images are taken from the Recurrent Neural Networks cheat sheet that you can find on the official Stanford website. And I will put the link in the description for you. Now, how do RNNs learn? And basically the same as other neural nets, they learn by the backpropagation algorithm, and to be more specific, by backpropagation through time. So we do a full forward pass through all the time steps, and then a full backward pass through the entire sequence and calculate the gradients. So nothing really special here. And by the way, if you want to learn more about backpropagation in detail, then we have another video for you on our channel that we link here. Now, this long way of traveling can have one major problem. The more layers we have to travel through, the more multiplicative gradient calculations we have. And this can lead to a so-called vanishing gradient or also to an exploding gradient. And this in turn means that these information get lost and it gets difficult to capture long-term dependencies. So the more time steps we have, the less information we can keep from time steps that are further in the past. So let's again have a look at the two sentences from the beginning. The color of the sky is blue, and I grew up in Germany, that's why I'm fluent in German. In the first example, the relevant information are sky and blue, so they are close together. But in the second one, maybe we can guess the word should be a language because we see the word fluent. But to guess the correct language, we also have to read the previous sentence. So we have to go further back in time. So the more we have to go back, the more difficult it can be for our RNN because of this problem with the vanishing gradients. But luckily, there are existing solutions that tackle exactly this problem. Long short-term memory, or LSTM, and gated recurrent units, or GRUs, are two special variants of RNNs. They are capable of learning long-term dependencies using a mechanism called gates. So they often outperform simple RNNs and are important to know, but getting into more detail here would be too much for this video, but I'm sure we will cover them in a later video in the series. But also having these two improvements does not mean that simple RNNs can be skipped, because on the downside they are computationally much more expensive, so in many cases a simple RNN will be just fine. Now at the end I also want to quickly show you how you can use this in code. So both deep learning frameworks PyTorch and TensorFlow make this pretty easy for you because they have existing layers that you can use. For example, here is the PyTorch code. So here you can set up this RNN layer and you find this in the torch.nn module. And the same way you will also find the LSTM and the GRU layer. And then what is important to note is that when we call this layer in our forward pass, we also have to put in a hidden state. So here we initialize the hidden states with a zeros tensor, and then we pass it to our RNN layer. And then we get two things back. One is the output and one are the encoded hidden states. So yeah, this is how it works in PyTorch, and in TensorFlow the API looks different. But here again, you have the layers already available. For example, you can use the simple RNN, or also LSTM and GRU are available. And then you can put this in for example, a sequential model. All right, I hope I could explain RNNs in a simple way. If you still have questions, then let me know in the comments. If you enjoyed the video, then please leave us a thumbs up and consider subscribing to our channel. And then I can recommend to watch this video if you haven't already, about backpropagation. And then
So in this video, let's learn about recurrent neural networks, how they work, how they learn, and also some of the improvements that were made on them over time. So let's get started. A nice thing to do before to start talking about RNNs is to remember how neural networks look like. So if you remember, in a normal neural network, or a deep neural network you can call it, we have an input layer, a hidden layer, and an output layer. And information runs sequentially. So first the information comes to the input layer, then it is passed to the hidden layer, and then finally the output is produced. So all of the data points that you have, you give them at the same time, all of the features of your specific data point that you're training on. The difference in neural networks of recurrent neural networks is that they are recurrent. So that means that the same thing happens over and over again in a way. So this is what a recurrent neural network looks like when it's unrolled, and I will also show you the rolled form. But basically what you need to know is that each of these little sections are actually one of the same. They're the same network, or they are the same neurons. So what happens is, these are all the different input features, and you give them one after another. So you first give the first feature of your input, and output is calculated and also passed to the second time step. We call them time steps. And then the second feature of your input, data input, or a data point, is given, including the output of the first one. Another output is calculated, and so on and so forth. So when you put it in, when you show it as it is actually, and how it is that it is just one unit. So what happens is, you give it an input, output is calculated, but at the same time output is passed again. The second feature of the input is given. So when you compare it to neural networks, what happens is, in neural networks you give all of the features at the same time, whereas in recurrent neural networks you give all of the features one step at a time. So it is basically, things happen in a time step manner. So we would call this the first time step, the second time step, third, fourth, and fifth time step. So basically, in each of these time steps, except the first one, you have two inputs. One of them is the output from the previous time step, and one of them is the input of this time step. So how do we calculate the output of recurrent neural networks? Well, we do it with this formula. It's actually quite simple, even though it looks like a complicated math formula thing. You have weights for your inputs. So for each time step, you have the weights. And for all of the outputs from the previous step, you have another set of weights. And you also have the biases. All of this is of course passed through an activation function, and at the end you have the output of your recurrent neural network. One thing to understand here is that even though it looks like we have many steps, as I said, it's actually just one unit. So Wx and Wy, which are the weights of the output of the previous layer and the input of this layer or time step, is the same, because they're actually the same. Here we're just showing them in an unfurled way because it's easier to understand. So there's only one set of weights for the input and one set of weights for the output. So there is a very common way of showing cells of RNNs, because these cells here, how the output is calculated, can be different. And we will talk about different types of cells too. But let's talk about how to depict a simple RNN cell. So what we normally have, of course, as we talked about, the output from the previous step, time step, and the input of this time step. So these T's basically depict this time step. T is this time step, T minus 1 is the previous time step. So to show this formula on a diagram, we can say, okay, there is a multiplication happening here. This is multiplied with Wy, and here another multiplication, and this is multiplied with Wx. And then we also add the bias here, so that's why the crosses and the pluses here. And this all goes through an activation function, of course, and very commonly what's used is the hyperbolic tangent function. But of course you can use other things too, but generally hyperbolic tangent function is the one that is being used with simple RNNs. And at the end we pass the output of this time step to the next time step, and also we output it. But Sometimes this is not the case. So for simplest of RNN cells, this is the case where you pass the output to the outside world and also to your next time step. But sometimes you do an extra step on before you output something. So you maybe pass it through a softmax function if you want it to be between 0 and 1 instead of -1 and 1, because that's what the hyperbolic tangent function where it will produce. Then basically what you pass to the next state will not go through the softmax function, that extra step, and then you will still pass it to the next function, next time step. So it still is the same thing, but has seen less processing. So then what happens is we call this the hidden state of this time step. So the hidden state of this time step is passed to the next time step. So this is just a interesting difference to keep in your mind, that you do not always just pass the output that you get to the next time step, but sometimes we call it the hidden state. There are, of course, a bunch of ways how you can use this architecture, because you do not always have to pass all of your output all of the outputs that you calculate in your cells. So let's look at a couple of different options. The first type is sequence to sequence RNN model. So basically for every input that you give in each time step, you get an output for that time step. And for these kind of things, you can use for things that where you're forecasting things. So for example, price forecasting or stock exchange forecasting sort of things. The second one that you can use is called sequence to vector. Sometimes it's called sequence to single, because you only get one output at the end of the whole RNN network that you have. And these things that you use for, let's say you have a sentence or you have an email, and at the end of or as an output of the model, what you want to know is it scam or not? Or for example, sentiment analysis, like what kind of sentiment does it have? Is it negative or positive? That kind of things. So for that, in each time step, you give your network a input, and then you just ignore the outputs. Even if it's producing the outputs, you do not look at them. The only output that you look at is the one at the end, because before seeing the whole sentence, your model cannot come to a conclusion, of course. Another one that you have is vector to sequence, or as I said, single to sequence. By the way, the reason that they are not called single but vector here is that because the output that you have is in the form of a vector most of the time, and it is not just a single number. That's why we just call it vector instead of single, but both ways are fine. So in vector to sequence sort of architectures, what you're doing is you're giving the network one input, and you are letting it output a sequence of things. So this could be, for example, you give your network an image, and then you're having it output a explanation of that image word by word. So let's say you give a photo of a dog running on a beach. Then for each of these time steps, the network will output a dog running on the beach, for example. So those are the kind of things that you would use a vector to sequence architecture for. And lastly, we have encoder-decoder sort of architecture. So in these kind of architectures, RNN architectures, at first you are only giving your network inputs. So input for a couple of time steps, or how many ever that you need. And then you get outputs. So, and then in the second part, you only get outputs. You do not give any inputs. And these kind of architectures are good for translation, because to translate a sentence, your network needs to see the whole sentence first, because meaning of some words might change, the translation of some words might change if you see the whole sentence based on the context. So that's why you first give it the whole sentence, and then you give get the translation word by word on the decoder part. All right, but how does RNNs learn? So how does the training work? It's actually quite simple. It's very similar to normal neural networks that do not have any interesting architecture, but we just call it backpropagation through time. So what happens is the output of the network is calculated, of course, and we do it you can think of it as like its unrolled form. So at first you give it input as 0, and then, or the hidden states from the previous time step, because it doesn't exist as 0. You give the first input, you get a first output. You give the second input, you get a second output. And then you just calculate whatever you want to calculate. And then we calculate the cost of this network. But as we said in the previous slide, sometimes the network, how you use the network might change. So you might want to ignore the first couple of outputs, or maybe you're just interested in the last 2 outputs, or maybe even you're just interested in the last one. So based on that, the cost is calculated. And then based on that, as we did with normal neural networks, we calculate the gradient, and then the gradient is passed back through the network, and the weights are updated. But as we said, all the weights of all of these time steps are actually the same because they're actually one time step. And then the gradients are calculated as we do with normal neural networks, and then these gradients are passed back in the network to update the weights. But as I said, you might ignore some of the outputs while you're calculating cost, so the gradients are passed back only through the ones that you used in the cost calculation. So RNNs are actually really good for analyzing sequential data, so this could be time series data, text, or audio files, for example, but of course they have some shortcomings. So the first one is that they have unstable gradients. And you can imagine that, right? Because it's a very long sequential sort of architecture. So the further back you go in this architecture, the smaller your gradients are going to get. So you might not be able to update the weights on the previous timestamps in a way, or to previous time steps in a way that will be helpful for the whole network. What you can do for this problem in RNNs is use other techniques that we use for normal neural networks too, or just deep neural networks too, to deal with unstable gradients. Or you can use layer normalization instead of batch normalization, because batch normalization is not as effective with recurrent neural networks. So they're kind of tricky to apply to recurrent neural networks. So instead you can use layer normalization. And another problem with simple RNN cells is that they forget. If you give it a very long sentence, it tends to forget what was being said at the beginning of the sentence. So the applications that are created with it are not really effective, or they don't work as well. So instead we have the LSTM or GRU cells that we can use to make sure that we still remember the beginning of a sentence at the end of it. So let's see what a LSTM cell looks like. If you remember how I showed you in that diagram, the RNN architecture, the simple RNN cell looks like, it will be easier to understand this one here. So what we have is a couple of sigmoid activation functions, and then we have another hyperbolic activation function. And we here see that there are two hidden states that are passed from the previous time step to us, and then we again pass those two different hidden states to the next time step. And then we again have an input, and then we have an output. So let's look closely what all of these things mean. So the first things that we need to understand here is that, as I said, we have two hidden states coming and going to the previous and next time steps. The first one is the previous one, as we talked about, is just a hidden state from the previous step. But the other one, C, is a long-term memory hidden state. So basically, as you say, there are less things happening to this hidden state, and we either forget or add some things to this long-term hidden state, and it passes to the next time step without much coming out of it or going into it. Why do I know, or how do I know things are being added or extracted from these time steps? Well, because we have the forget gate here, we have the input gate here, and we have the output gate here. So basically, these are the gates that create the information workflow, or how this information is used in this specific time step. So let's talk a little bit more in detail about that. So what we have here are called gate controllers. So anything other than the hyperbolic tangent function, we call the gate controllers. And what the gate controllers do is they either input 0 or 1. And in this way, they determine if something is going to be forgotten, if something is going to be input, or if something is going to be output from the long-term state. And how this works is basically in the forget gate, we decide which part of the long-term memory should be removed from the long-term memory. So, we're saying, okay, this can be forgotten now. We don't need to remember this information anymore. In the input gate, we decide which part of the hidden state or the information that we just added to the hidden state needs to also be passed on to the long-term memory. So we're deciding, okay, actually this piece of information is important to remember later. And in the output gate, we decide which part of the long-term state we need to extract from the long-term state right now and use as an output, either as in the hidden state to pass on the next timestamp, or as an output in this, or as part of the output that we generate in this timestamp. So it sounds kind of complicated, even though it's sort of intuitive that there is one long-term memory, one shorter-term memory, and then we either forget things from the long-term one, either use it or add new things. And it's kind of confusing to understand, okay, but like how does this thing whole work? Why do we forget input, or how does the forgetting and inputting happen? But you don't have to understand everything behind it. You don't have to understand how it's all working. Basically, what you need to know is that it is working, and this is the intuition, and I think that will get you where you need to go. So you don't have to obsess over how this whole works. So another different kind of cell that we have is called a GRU cell. GRU cell is basically like a simplified version of the LSTM cell. You know, you have less things happening here. You do not have a separate output. As you can see, the hidden state that is passed to the next time step and the output is exactly the same. And here the gate controller R decides which part of the previous state will be shown in the main layer. So main layer being the one where we pass through the hyperbolic tangent, and basically the main state that is being passed to the next time step. The R decides which part of the previous state that we got from the previous timestamp is added to the timestamp and the output of this, or the state and the output of this time step. And that's it. That's kind of like a first step at RNNs, kind of beginner level information that you need to know. If you want to learn more about RNNs and deep learning in general, go check out my course, Deep Learning 101. I will leave the link in the description below. Before you leave, don't forget to give me a like and maybe even subscribe to show your support. I would also love to hear your opinions about this video or any questions that you have in the comment section below. But for now, thanks for watching, and I will see you in the next video.
Okay, so last one is deep belief networks. It is comprising multiple layers of stochastic latent variables. DBNs are used for unsupervised learning and feature representation and high dimensional data domains like images. So these are the deep learning algorithms for image recognition, the CNN, the RNN, and the DBN. So that ends our presentation. Thank you for listening.